right, this is so exciting. It's the last lesson of the last chapter. Oh my gosh, we're finally there. 12-3, inference for slope. I would like to apologize for the sound in the background. It is my washer. It is loud, and I really hope it doesn't bother you. Yeah, it's going on right now, so can't do much. All right, so inference for linear regression. Remember linear regression? That was from chapter 3. Yikes. Okay, so least squares regression line. Remember, this is the least squares regression line. And this is the population least squares regression line. So in other words, they took all the eruptions, Old Faithful eruptions, the 263 eruptions in a single month, and they plotted it. So the population is all the eruptions in a single month. Okay, and then they found this linear regression line that fits the least squares regression line, that fits this population data. And this is like our ultimate goal. We want this. So this is going to give us the most accurate predictions for that specific month, for example. So using a sample linear regression, we should be able to estimate that line. So if we took a sample from this population, let's say this many, and we plotted that and did the linear regression line, we're trying to estimate the slope of that line to this line, the population line. We're using the sample slope, we're using it to be able to estimate the population slope. We really don't care about the y-intercept because as you could see, as you remember, hopefully from chapter 3, sometimes the y-intercept is irrelevant or useless information, or doesn't make sense in the context, like weight being negative pounds or something like that. So the y-intercept really doesn't tell us much, but it really does help to know the slope, because that tells us how fast of a rate this thing is increasing. Okay. All right. And so in chapter 3, it was this. It was y hat equals a plus bx, where this was the y-int and little b was the slope. We used to write it in this format here. Okay, and now we have one for the population. And the population is, instead of y, it's mu y sub y. It's the mean y value. The mean y value for a given value of x. Given value of x, it's the mean y value. This is the population y-int. Oh, don't write this on the test like this, by the way. Somebody in class was asking, can we say pop for population? I was like, no, please don't do that on the test. And then this is your population slope. And so alpha, I know, like don't confuse it with the alpha significance level alpha. Obviously, this is related to linear regression. And now we have beta. Yay. So beta is the population slope. Love all the Greek letters. Yes? All right. Here is our scatter plot. An example of a scatter plot. One sample scatter plot, and that blue line is the population one. This lighter green one is the sample one. Blue line is the population, the lighter green is the sample one. Notice how the lighter green is constantly like being close to that blue line, but it's not exactly the blue line. So every time we take a sample and we do a linear regression model on it, we get close to that blue line, but we're not exactly on it. But if we kept taking it over and over and over and over and over and over and over again, then the slope of all of the sampling distributions would come out to be approximately normal. But because we don't know sigma again of this population of slopes, we're going to use a t distribution instead. Okay, the conditions are a killer here. Oh my God, extra conditions, as I have remarked. And this actually, I think I put it here somewhere. Did I? Yes. All the conditions I'm going to go over again later, but there are definitely extra conditions. Linear, we're going to look at whether something is linear, independent, like the data is linear, I mean. Independent, and that's your 10% condition. Normal for the residuals, equal SD, and random. Random is the easiest one. So at least at the very end, we're done with the easiest one. So let's take a more detailed look at each of them. Linear, meaning we're going to look at the scatter plot. The scatter plot should show a linear pattern. This is a linear pattern. They're kind of all aligned in a row to make it look like a little linear, roughly linear. All right. But we also have to look at the residual plot. For the residual plot, make sure there are no leftover curved patterns or any kind of leftover obvious patterns, as like I like to call it. It doesn't only have to be curved. It just can't have an obvious pattern. And here you could see there's an obvious pattern. Like, no, this one doesn't work, okay? So this is bad. This is a bad residual plot. You would say you would fail in this case. You would not do the inference for slope with this particular data if this was given to you. Independent is our 10% condition if sampling is done without replacement, or if you are doing, you can also say knowing the value of the response variable for one individual shouldn't help predict the value of the response variable for another individual. But if it is a sampling done without replacement, you do the 10% condition. You're going to make a histogram or a dot plot or a stem plot or a box plot of the residuals. Okay, and so looking at the residuals, I'll show you an example of that later. A lot of time they give you this, but if they don't, you can make a dot plot or a histogram or a stem plot or all those possible graphs for residuals. And what you're looking for is no strong skewness or any obvious outliers. And then equal SD is hard for me to explain. I've always had a difficult time explaining this. I cannot deny this. But basically saying, see how randomly like they look like they're kind of evenly distributed around this straight line? So that's what you want to say. But you don't want to say this straight line in the middle. You want to say at the residual equals 0 line, all the points are about evenly spread out around this one line, the residual equals 0 line. These are not. Notice that the equal SD, like these are closer, and then these are farther apart. Well, also makes sense that you probably will have equal SD if you have not failed the linear aspect. But I haven't thought of a situation, which I have to look this up, where it's linear, passes the linear, but then fails the equal SD. Would it ever do that? No idea. I'm going to have to look at that. Because technically, when you look at this, there's a leftover pattern here. So technically, this is not good. Random is easy. Is the sample taken randomly? Yep. And that's it. So all the conditions actually spell an acronym that I find easier to remember, and it's LINER. LINER, we love acronyms. Linear, independent, normal, equal SD, and random. So we can't use sigma. We don't have the sigma usually. So we're going to use the standard deviation of the sample. And in that case, this is the standard error of little b. So the standard error of slope is using this formula with the standard deviation of the sample. And in that case, we're using for the critical value, we're going to use T star then, since we are using standard deviation of the sample. This is very similar to what we did before. We have a test statistic, and this test statistic is B here, the slope, the sample B, sample slope. We have plus or minus in the middle here, and our T star is our critical value here, and then our standard deviation of the statistic is the standard error of slope. I think I called this test statistic. This is technically just statistic. I apologize. But the statistic, meaning, you know, in the past, p hat, we had x bar, and now we have little b. So those are the three statistics that we have learned so far. We have learned many more too, but with the inference section, I mean. And our degrees of freedom is n minus 2. Degrees of freedom is definitely n minus 2. That's probably because of two variables. So n is in the sample size minus 2. We're going back to sample size here, not categories. Categories was for the chi-square test statistic.